We are going to look inside a 16-bit quantum state. At this scale, the math requires tracking 65,536 distinct dimensions simultaneously. If we take a known search algorithm and run it backwards, mathematically reversing the process, something highly unusual happens to the system's entropy. We expect chaos to increase, but instead, the two standard measurements for entropy completely split. This chart shows the observational, or Shannon entropy of our quantum system. When we begin reversing the algorithm, the uncertainty of our observation rises from 0 and converges exactly at 16 bits. But if we plot the von Neumann entropy on the same axis, we get a flat green line stuck at 0. The system is reaching maximum observational chaos, yet physically the information remains perfectly preserved. This divergence between what we observe and what is physically conserved is the central phenomenon that the topic ledger theory attempts to map. To understand how this split occurs, we have to unpack the exact computational architecture required to simulate this reversal, beginning with the BigQuery pipeline that logs the events. Before we can run the reversal, we need an immutable ledger to record every irreversible step. We establish a directed acyclic graph, or DAG, in BigQuery to log these computational events as they happen. To populate this ledger, our first pass uses variational quantum algorithms to search a 16-bit space for a single key. The search fails. Cryptographic parity offers no smooth gradient. The model gets stuck on a barren plateau, guessing blindly. We replace the guessing model with a rigorous approach. Using the Bernstein-Vizirani algorithm, we locate the exact 16-bit key in exactly one iteration. In a cryptographically complex space, locating a target requires deterministic quantum math rather than heuristic approximations. However, the Bernstein-Vizirani algorithm only resolves linear functions like XOR. Real cryptographic hashes are highly nonlinear, which renders that approach useless for this test. We have to use Grover's search algorithm instead. Grover can execute nonlinear pre-image attacks, and for a 16-bit space, it finds the target in exactly 201 iterations. But modeling a nonlinear hash on a quantum computer has a structural cost. Because quantum mechanics forbids destroying information, every AND gate requires extra Toffoli gates and ancilla qubits to hold temporary data. Simulating this classically causes an exponential memory explosion. 16 qubits needs 1 megabyte, 50 qubits requires 16 petabytes. Holding the state vector for a large quantum circuit requires rows of enterprise server architecture, which exceeds the capacity of standard consumer hardware. Physically composing a 16-bit nonlinear hash oracle creates a reversibility bottleneck that would normally overload a GPU's memory. We need an engineering workaround to run a 201-layer Grover search on classical hardware without triggering a memory crash. Instead of physically building a chain of tens of thousands of gates, we translate the operation. We update the state vector directly by condensing the logic into a single matrix multiplication step. Using the evolve method, the computer updates the mathematical state without retaining circuit history. RAM usage stays completely flat. The state converges on the target. The 16-bit hash is cracked, and the final state is logged into our BigQuery ledger. We now have a perfectly converged quantum event. The system is in a pure state, ready for us to reverse the process and observe the decay of that certainty. In this framework, the cracked 16-bit key represents a converged reality. Because there is 100% certainty regarding its state, the Shannon entropy is exactly 0. Now we initiate quantum retrodiction. By applying the inverse Grover operator, we rewind the assembly index, removing the causal history from the ledger one step at a time. As those causal events are removed, the observational certainty dissolves. The probability of the state diffuses across all 65,536 possible outcomes. The system reverts to the everything pool, a state of maximum observational uncertainty, where the Shannon entropy reaches the 16-bit limit. Unwinding the ledger removes the specific context of the topic, returning the system to a uniform superposition of all 65,536 possible histories. This returns us to the initial paradox. If the observation is dissolving into chaos, why does the von Neumann entropy remain at 0? The answer lies in how John von Neumann defined the entropy of a closed quantum system. The Grover operation is unitary. The underlying quantum state is never destroyed. The vector simply rotates through Hilbert space, its physical integrity remaining constant.
Von Neumann entropy measures this vector's purity.
while Shannon entropy measures our ability to predict a single outcome. In this model, the universe conserves every bit of raw physical information, but observational reality only exists when that information is assembled into deterministic ledgers. By reversing that assembly, the topic simply dissolves back into the background noise of the everything pool.